On this worksheet, we're going to be practicing the acid-catalyzed hydration reaction. First thing you might be noticing, what the heck is this D3O plus thing? D is the symbol for deuterium, which is just an isotope of the hydrogen atom. In terms of reactivity, deuterium and hydrogen behave the exact same way, so they are interchangeable when we're writing out a chemical reaction. Teachers just use the symbol deuterium as a way of sort of making sure that students know exactly where the different hydrogen atoms are showing up in the product of a reaction. So D3O plus is exactly the same thing as H3O plus in terms of reactivity. First thing we're going to do is propose a mechanism for this reaction. I'm actually going to draw out the structure of the D3O plus. It makes it easier to draw the mechanism. For this reaction, the double bond is going to reach out and attack one of the deuterium atoms and break the deuterium oxygen bond. That is going to cause, so the electrons in this double bond is going to cause the formation of a new bond to that particular deuterium atom. And that deuterium atom is going to end up bonded to one of the two carbon atoms that were originally in the double bond. This is going to follow Markovnikov's rule, which means that deuterium atom that we're adding is going to want to position itself onto the carbon atom that has the most hydrogens already present. That gives us the more stable carbocation. Anytime we do a reaction that forms a carbocation, we always want to immediately think about the rearrangement of that carbocation to form something that is more stable, which would be this tertiary carbocation right here. Now, after that carbocation has been rearranged into something that is more stable, our water molecule, which is a deuterated water molecule, D2O, the lone pair of electrons on the oxygen are going to attack that positively charged carbon, which is going to give us an intermediate. It looks like this. We actually refer to this as a protonated alcohol because it's an alcohol molecule that's got an extra hydrogen on it. And then we're just going to finish this reaction up by removing that extra deuterium. We could do that with another D2O molecule. Just grab either one of those extra deuteriums, break the deuterium oxygen bond, and that's going to give us our product, which matches up with the product that was provided at the top example. Now we just have a couple of questions. Does this reaction follow Markovnikov's rule? Absolutely yes, it does. When we add that first deuterium, we're placing it onto the carbon atom that had the most hydrogens present and forming the most stable carbocation. What is the stereochemistry of the products of this reaction? Well, since we are adding the D2O, the water molecule, we're adding that to a carbocation. That means that we would get, if we had stereochemistry, we would get a racemic mixture of products. In this particular example, we don't get any sort of racemic mixture because we don't have any chiral carbons. So maybe I'll put parentheses around it because this particular molecule can't be a racemic mixture, but it's going to be 50% R and 50% S if you are forming a chiral carbon in the reaction. Could this involve the rearrangement of a carbocation? Yes, we saw. Anytime there is a carbocation formed, then absolutely yes, we always want to think about rearrangement.